Well, good morning, stats students. Hope you're having a good day so far. Let's get started. Before I get started, I want to make sure that you know that these are available online. Bobby can show you where she's getting them. There's a link to these on the class website. So if there's something you missed, or if you just want to hear something again, you can watch it again. Or just watch the part you like, because I'm flattering myself that these are so wonderful. You're going to want to watch them again. Anyhow, forgive me if I have a cough or a scratchy throat. I've got a little bit of a cough here, so moving on. We're going to be looking at type 1 and type 2 errors that you can get in hypothesis tests. But before we do this, as review, plus it also leads into what we're going to be doing, I'm going to ask her to pause this video for 5 minutes and take out your notes. And here's a problem I took a picture from another book. And I want you to just work out this complete hypothesis test: assumptions, conditions, conclusion, the whole 9 yards for practice, plus it helps review and get your mind ready for what we're going to be doing. So pause for 5 minutes here. Okay, so let's go through this together. First, we're going to write our hypotheses. I'm going to let P represent the proportion that we're interested in. That's, it says here, is it reasonable to conclude that more than 3/4 of adult Americans plan to alter their shopping habits if gas prices remain high? So that's the population proportion that we're interested in. The proportion of Americans who plan to alter their spending habits if gas prices remain high. I'm just echoing the prompt. So, got our null and alternate hypothesis. Our alternate hypothesis is that it's more than 3/4, greater than 0.75, are going to plan to increase their spending habits or change their spending habits. And then the null is, of course, the equals. No, it's actually just 75%. So that's our null and our alternate hypothesis. And you can write them this way as long as you've defined what P is representing. And the stress here is that it's the population that we're interested in. So now we're going to check our assumptions and conditions. First assumption, simple random sample. The problem says we're going to assume that the sample is representative. That's basically saying that it's acting like a simple random sample. P is constant. Certainly our sample size of 1,813 is less than 10% of all Americans. So that's who we're interested in. Actually, adult Americans, but it still works. And then finally, the normal model, that also checks N times P and N times Q. Actually, this is P, this is Q, but it doesn't make any difference when I write it over here. These are both clearly more than 10. Our sample size is quite large. So we're good. Our assumptions are reasonable. All the conditions all check. Mechanics of the test. So here's a nice little normal distribution I clipped from online. A little picture of our sampling distribution by null hypothesis. On average, 75% of a sample by null hypothesis will say that they plan to change their spending habits. Not every sample is the same, so we're going to need sigma p hat, and that's root pq over n. Calculator tells me that's this value, 0.01017. Now I want to know what's the z-score from my observed proportion. My observed proportion is 1,432 out of 1,813. So z-score is observed value minus expected value over the standard deviation. I observed 1,432 out of 1,813. I would expect, by null hypothesis, 75% to say they were going to change their spending habits. Divide by the standard deviation computed above, that gets a pretty big z value, 3.92, way out here. So it looks like we're going to reject our null hypothesis, because the area to the right here, which we're shading to the right because of this right there, greater than, it's going to be pretty small. And the probability that a normal z-score will be greater than 3.92, I would be that shaded region here I'd shade, but there's nothing to shade. I mean, it's just a little sliver. I used an online calculator that tells me that's 0.00004. Your calculators will probably give you more significant figures than that. It's a norm CDF calculation. And so I write my conclusion with the p-value of 0.00004, which is less than 5%. We reject the null hypothesis and then conclude that the proportion of Americans who plan to alter their spending habits of gastropane high is greater than 75%. I ran out of space there. I'm just echoing the alternate hypothesis, which I'm accepting because I've rejected the null hypothesis with my very, very low p-value. It's not likely I would see this happen, this observed p-hat or higher, if the null hypothesis were true. So I reject the assumption of the null hypothesis and conclude the alternate hypothesis is in all likelihood correct. So we can pause if you want to discuss it with one another, but I'm going to move on in the video. So pause if you want. So alpha levels and type 1 errors. So far we've been rejecting the null hypothesis. If we get this p-value under 5%, we saw that in the example problem, was a lot less than 5%. And that 5% was just a number I told you. It's like, okay, just choose this as sort of a magical line in the sand. Less than 5%, reject. Not less than 5%, fail to reject. What difference does it make if we change this cutoff value? I want to think about what the meaning of this 5% that we've been using. Excuse me. So here's our sampling distribution. Remember, the p-value is the probability of getting our observed p-hat or higher if the null hypothesis were true, and it's based on that assumption. It's really important to understand that where p-value is based on an assumption of the truth of the null hypothesis. If the null hypothesis were true, given that, then we would see whatever p-hat we compute or higher, the probability of getting that value is the p-value. Now, I said higher here. It would be replaced with lower if our alternate hypothesis was a less than alternate hypothesis rather than a greater than. But I'm going to draw my pictures and talk as if it were a greater than for the rest of this lesson. It doesn't change the ideas, it just changes the pictures. Everything gets flipped around over here. So we've got in the middle of our sampling distribution the p from our null hypothesis. We're assuming that to be the case. And let's say we do a sample or an experiment or something, and we get a computed p-hat, which is higher than expected by null hypothesis. So the area off to the right would be the p-value. That's just what I'm just drawing a picture of what I'm saying over here, what the p-value is. It's the probability of getting our observed p-hat or higher, that area. So that is the p-value right there. Now, let's say we have our cutoff value is 5%. So if you use your calculators, you can work this out. I'll do it as a little quiz list later. There's a certain z-value in the normal distribution which cuts off precisely 5%. So the area to the right of this line is exactly 5% of the area under the normal distribution. So that means, let's think about what this means. That means that if I were to get a p-hat from my sample or from my experiment that landed out here someplace, either near here or much farther out, and then if I were to shade the area to the right, I would be less than 5%, because this area to the right of this line is exactly 5%. What this means is if p-hat lands out here, I will reject the null hypothesis. This line is the cutoff line for z-scores, or for p-hats. If I get an observed p-hat out here, I will reject the null hypothesis, because its p-value will be less than 5%. So I'm calling this the reject region. If p-hat lands out here when I draw my sample, I will reject the null hypothesis. And likewise, if p-hat lands over here, then I will fail to reject the null hypothesis. Then my p-value will not be less than 5%. And in fact, the one that my example I drew with this pink here, it looks like I would fail to reject because the area here is slightly more than the 5%, which is to the right of the green line. So this p-hat that I drew at the beginning is in the fail to reject region. So if I compute a p-hat and it's out here, I reject. Out here, fail to reject. This is all just idea building here. You don't actually have to compute this magical value when you're doing a test. So here's the big question. All of this was based on the assumption that the null hypothesis was true. But what if the null hypothesis really is true? What if this thing that we're pretending for our computing, what if the null hypothesis really is true? What if p really is equal to the null hypothesis value? Well, let's think about what that means. That means that in reality, this is the actual sampling distribution. This is when you draw a sample, you get a p hat from this distribution. It might land here, it might land here. It's more likely to land in this region than it is to land down here, or land down here. However, what this means is that 5% of the time, we will get a p hat that lands to the right of this line. That's exactly what alpha is. It's that 5% out here. So that means that we will reject 5% of the time, purely by chance, but we shouldn't have. The null hypothesis was really true, and we made a mistake. And we didn't make a mistake like we did our computations wrong. We simply, by bad luck, got a p hat value that happened to land in the reject region by chance. It just happened. And so that means that the alpha here, the 5% that we've been choosing, is the probability that we will reject the null hypothesis when the null hypothesis is actually true. So that's what I say on the next slide. A type 1, and what I'm describing here is a type 1 error. Type 1 error is you reject the null hypothesis when it is true. It's a conditional probability. If the null hypothesis is true, given the null hypothesis is true, you reject it mistakenly when you shouldn't have. So the 5% we've been choosing is called the significance level. Just going to let this type out here. The 5% we've been choosing is called the significance level or the alpha level, and it is the probability of a type 1 error. It's the probability of rejecting the null hypothesis given the null hypothesis was true. You made a mistake. It wasn't a mistake in computations, just by chance. So if the 5% is the probability of a certain type of error, of a type 1 error, then why not just make alpha really, really, really tiny, then minimize the probability of having this type 1 error? And you might be able to guess, just based on the fact that it's called a type 1 error, that there's another type of error. And they go against each other. If you make alpha really, really small, then it increases the probability of that other type of error. So we're going to look at this other type of error right now. Oh, I've had some more. There's another type of error. So now this slide can get a little bit hairy here, so I'll try to explain things clearly. We're going to talk about type 2 errors, very creatively named. So here's my null hypothesis. Here's my null hypothesis sampling distribution. It turns out, I was going to give it to you as a quiz, but I just gave it away. I don't care. It turns out that a z of 1.645 cuts off 5% of the area under the sampling distribution, under the normal curve. So this is now exactly 5%. I tried to draw this green line at around a z of 1.645. So that corresponds to an alpha of 5%. This area is 5% of the total area under the curve. So if we get an p hat out here, we'll reject the null hypothesis and accept the alternate. If we get a p hat over here, we'll fail to reject the null hypothesis, and we will fail to accept the alternate. Now here's where it gets a little bit crazy. Up here we've got the null hypothesis distribution. And we've got the p at the middle of this. The p is the null hypothesis value for p. Like in our warm-up problem, it was 75%, 0.75. What I'm drawing down here is a picture of the actual distribution. So I want to make it clear. This is what we're assuming is true by null hypothesis. but it might not be the reality. The reality might be different. Here, notice I've put at the middle a value that's higher than our null hypothesis P. So here's our actual distribution. And we don't know what this looks like. And, we wouldn't be doing the hypothesis test, if we knew the actual value of P. But we have to think about, we're going to draw a picture of it as if we knew it, so we can understand the consequences of changing alpha and these other types of errors. So, let me make it really clear. This is our null hypothesis distribution. This is the sampling distribution we use when we do the test. This is the picture we draw. There's our null hypothesis P at the middle, and we'll use here. Down here, however, is what's really happening. When we actually draw the sample, we're drawing it from this distribution, because this is reality. So this is the distribution we use when we're making our calculations. This is our alpha level, alpha and our shaded. We'll draw a picture like this, and we'll get z-scores, and we'll use this distribution up here. But unknown to us, we're drawing our sample from this distribution. And in this distribution, the actual value of P is higher than the null hypothesis. So we should reject the null hypothesis here, because P is higher, the actual P is, excuse me, higher than the null hypothesis P, and that's what we're trying to test for. So, I'm shading a region over here. Remember, this line here was drawn based on the null hypothesis distribution. There's my 5%, because all this is true by assumption, pretending that this is true. Reality, we're drawing from this distribution. So here's my fail to reject region over here. If I get a P hat in this region, I will fail to reject the null hypothesis. Now I'm drawing from this distribution. This is reality. Again, true by null hypothesis, reality. So this is reality. So this shaded region here, that I shaded red, that's the probability I fail to reject. Let's think about it. This is the actual distribution I'm drawing from, this normal distribution. This is the fail to reject reason here. So this is the probability I fail to reject the null hypothesis. But I should reject the null hypothesis. It's false. Look. The actual P is greater than my null hypothesis P. The alternate hypothesis P is greater than the null what I was assuming. So I should be rejecting it, and if I get it, if I draw one from here, I fail to reject. So I've made an error. Okay, that's called a type 2 error. When you fail to accept a true alternate. Okay? I should have accepted it. I should have rejected the null. I should have accepted the alternate, and I didn't. And I should have, because the whole time the alternate was actually true. The probability of a type 2 error is given the label beta to go with the alpha we had earlier. So this shaded region is beta, just a certain probability. And beta is uncomputable if you don't actually know P, and you normally don't. So you may be saying, why are we talking about it? Because we have to understand the trade-off between type 1 and type 2 error, and there's something else we need to understand. So now I'm shading this blue region over here. Over here I've got beta on the left. The blue region is the probability that I reject the null hypothesis, because it's to the right of my line. It's in my values over here are in my reject region. So that, of course, is 1 minus beta. This is beta right here. This is 1 minus beta on the other side. And that's the probability I accept the alternate, given that it's true. So this is good. This is what I want to happen. In this case, I want to accept the alternate hypothesis. So this is called the power of the test. It's the probability of rejecting the null and accepting the alternate when you should, given that the alternate was true. And we like tests with high power. When the alternate should be rejected, we want to actually reject it. High power is a good thing. So I'm going to copy and redraw the stuff from the previous slide. and it's actually redrawing everything I did. It doesn't just do a copy paste. And I want to, because we're going to do some alterations here. What we're going to look at here, it's going to look at, so if having a high power is good, how do I get high power? What makes power high? So we're waiting for this to draw it out. There we go. So there's my picture from before. How can I increase the power of my test? How can I make this blue region right here larger so that I have higher power? How do I improve the power of the test? How do I improve the probability that I will reject the alternate given the alternate was actually true? So first, I could increase alpha. Let's think about what that will do. If I increase my alpha, then that means I'm increasing this green area. And this green area is alpha. And we get to choose alpha. We've been choosing 5%. There's no reason we have to choose 5%. We might choose a higher value, say 10%. I don't know what this is. I just drew a line there. So, in doing that, we've moved this cutoff line to the left, and now we will reject more often. Now we've changed some of this from fail to reject to reject. So there's my increased alpha. So now, what was formerly red is now blue. Now before the red was in the type 2 error region, the probability of making a type 2 error, and now it's moved into the blue region, which is the power of the test. Of course, the trade-off here is if you're increasing alpha, alpha was the probability of type 1 error. So if you want to increase your power and decrease beta, you want to reduce the chance of a type 2 error, which is the same thing as improving the power of the test. You have to increase your chance of a type 1 error. So there's a trade-off. And of course it would go the other way. If I were to decrease my alpha, reduce the chance of a type 1 error, then this line would move to the right and have a new line here, and it would increase the chance of a type 2 error. So there's a trade-off. When type 1 errors go up, then type 2 errors go down, and vice versa. What's the other way to increase the power of the test? What's the other way to increase the blue region? So this is a little bit messy. I have to do a lot of erasing here. The other way I could do it, probably type 1 error is just alpha. The other way I could do it is I could increase my sample size. So that will tighten up these curves here. You're going to see me do some crazy drawing. So each of these curves will get skinnier. So here's my new null hypothesis distribution. And there's my new actual hypothesis. So there's the area, my alpha, maybe that's 5% of the area under the curve. And then I'll erase the old curve, put in the new curve. So you can see here now that the probability of a type 2 error has decreased dramatically with my larger sample size. I mean, there's a much larger sample, that's how it got so skinny. These are both still centered in the same place. My null hypothesis P is still the middle. The actual P, which is unknown to me, is still in the middle. But you can see now that the power has gone up a lot. It's nearly all the area. I'm not likely to make a type 2 error here. Of course, increasing n, this costs time or money. So bigger samples kind of take time or take money. So anyhow, let me summarize. So alpha is the significance level, and that's the probability of a type 1 error, which is type 1 error is when you reject the null hypothesis given it was true. Beta is a probability of a type 2 error, and that's when you fail to accept the alternate when it is true. So type 1 error is when the null is true. Type 2 error is when the alternate is true, and you do the wrong thing. 1 minus beta is the power of the test, and that's just the opposite of a type 2 error. It is when you accept the alternate when the alternate is true. So type 2 error is alternate is true. Given the alternate is true, you fail to accept it. Power of the test, given the alternate is true, you actually accept it. And the way we can increase the power, sorry, indulging myself a little lightning bolt there, is you can increase alpha or you can increase n. The disadvantage to increasing alpha is that it increases the chance of making a type 1 error, and the disadvantage to increasing n is it increases the cost. So hopefully this was reasonably clear. It's online. You can rewatch it again. And Bobby has your homework, and we'll collect that homework tomorrow. Thanks for listening. Bye-bye.